Hey everybody, welcome back to the channel and our last installment on Unit 3. And the last installment is all about periodic law. Now, we've been talking about the periodic table for a long time. I mean, since Unit 2, where we were classifying elements into metals versus nonmetals and metalloids. And then we talked about how their location in the periodic table determines their properties. Lots of talk about the periodic table, but really, like we've said in class, the periodic table is one of the greatest discoveries in the scientific world, especially for chemists. I mean, everything we know of based on matter lies within that periodic table. So of course we're going to talk a lot about it. And you've also started to kind of get the idea about how the periodic table is put together. So you know all of your alkali metals are in group 1, your halogens are in group 17, and you've seen a little bit about why that happens. But we're going to talk a little bit more about that today, and we're going to talk about periodic law. And periodic law says that when the elements are arranged in order of increasing atomic number, their physical and chemical properties vary periodically. Now, you started to see that in that graphing periodic trends dry lab that you were doing. So you were told to pick one trend from two groups. So you had one trend on the top row and another trend on the second row. And you were asked to hand graph one trend from each. And one of those trends or one of those properties represented a periodic property, whereas another one represented a property that was not periodic. And periodic means it's going to happen over and over again. So for example, I get my hair done periodically. Every 6 weeks, I go back to the hair salon, I get it done, and it's nice and bright. And then it fades, right? It fades and fades and fades, and it starts to grow out at the roots. Then I go back in 6 weeks and it's nice and bright again. And then 6 weeks goes by and the same thing happens. And then I get it done and it's bright again. That's periodic. There's a repeating pattern that's happening every time. And with increasing time, I should say. And that's what's happening with increasing atomic number on the periodic table, is we have these properties that are going to repeat themselves over and over again. And an example of a periodic property looks like this. So in the graphs that you made, hopefully you saw something that looked like this. Not exact, but something similar. And you'll notice that especially when you plot your peaks and valleys, so here's all my valleys. I have helium, neon, argon, and krypton. And I have my alkali metals, lithium, sodium, potassium, and actually I have group 13 elements kind of as little smaller peaks. I have boron, aluminum, and gallium. Transition metals get a little funny, so you're going to find they don't always follow periodic law. But when you have increasing atomic number, like that's listed here on the x-axis, you're going to find that there's going to be trends that repeat themselves beautifully. So whatever this trend is, whatever this trend is, it's very low at a noble gas. And it shoots up at the next period on the periodic table, the next atomic number. When I add one more proton to the nucleus, this property is going to increase. And then it's going to slowly decrease as it goes across. There's going to be a little anomaly along the way. But that trend is going to decrease in value until it hits a noble gas as we increase atomic number, till it hits a valley. And again, as you continue with atomic number, the trend is going to repeat itself. And it's going to happen again as atomic number increases. And it's going to repeat itself again once it gets to potassium. And then it's going to continue down again. You can predict where the next element would be. So after potassium is rubidium. Pause this video or just take a second and guess where rubidium would be. Well, rubidium should be somewhere up here, because as you can see, your alkali metals increase in this trend. Rubidium should be somewhere up here. And that's a periodic law, is as atomic number is increasing, you're going to see a repeating pattern. Some properties are not periodic, and here's an example of one that's not. So if you were to locate your peaks and valleys, you're going to see there's really no rhyme or reason as to where the elements are located. So for example, hydrogen and helium, it's low and then it's high, and then I have carbon, aluminum, I have zirconium all the way up here. So there's really no relationship or correlation between the properties. And you saw this in that It's All in the Cars Dry Lab. You had all those properties, but you really didn't know which ones to make your periodic table off of. And Mendeleev had that same problem because that's what he was figuring out as he did this, what trends were periodic and which ones weren't. And we now know the properties that are very, very periodic, and they're actually very important for elements alone because they tell us how they react with other things to make compounds. And the three most periodic properties that we have atomic radius, we have ionization energy, and we also have electronegativity. So you all should have graphed one of those in that graphing periodic transactivity because these are beautiful periodic properties. Let's go ahead and talk about atomic radius. So the atomic radius is 1/2 the distance between the nuclei of identical atoms that are bonded together. I'm actually going to cut to this slide first to show you what this means. So if I have two hydrogen atoms that are bonded together, the nucleus, of course, is in the center. So that's why I have this line starting right here at the nucleus, and I have this line right here at the nucleus. Those two nuclei are separated by some distance. And because this is a radius, is 1/2 of the distance between bonded atoms. So this right here is the atomic radius. It's 1/2 the distance of atoms that are bonded together. So in this case, this is for diatomic hydrogen or hydrogen bonded to itself. So what are the trends? Well, atomic radius is going to actually increase going down a group. So as I go down the alkali metals or down the halogens, you'll see that atomic radius increases. Why? Why do atoms get larger as you go down a group? Well, as you go down a group, you're actually adding more shells around that nucleus. And as you add more shells, energy levels, aka shells, the atoms are going to get much larger. So you're adding those shells around the outside. Remember when we did that, when we were counting electrons? So you have 2 electrons in the first shell or energy level. You have 8 electrons in the second shell or energy level. Once you add those shells, the atoms are going to get much bigger. Period trend, a little bit different. So as I go across a period, actually atoms are going to get smaller. So for example, let's see, lithium is going to be much bigger than neon. Why is lithium a much bigger element than neon, even though neon has more electrons? Well, it actually has to do with the number of protons in this case. So as you add protons to the nucleus, that nucleus is getting a more positive charge and it's becoming stronger. And since it's becoming stronger, it's able to pull that shell in closer. It's able to shrink the shell on the outside. Or as you add protons to the nucleus, that outermost shell is able to come closer because the nucleus becomes more positive. It becomes stronger. So it's able to pull those electrons in closer. So the increasing positive charge of the nucleus pulls those outermost electrons in the outermost energy shell closer. You could pause this to write that down, but I'm going to show you a picture next. So here's a great example. General trends. Notice the transition metals aren't here because, like we said, transition metals get a little funky. Normally, we just talk about these trends for the main group elements. So that's like your alkali metals and your alkaline earth metals, and then from boron's group all the way to your noble gases. So as I go down a group, we are adding those energy levels. We're adding shells, and therefore your atoms are going to get much larger. Hydrogen and helium only have one shell around them. Lithium through neon have two shells around them. This row has three, or this period has 3, 4, 5, and cesium's period has 6 shells that are around it. So that's a pretty easy trend. As I go across a period, however, notice that the atoms are getting smaller. And that's because you are increasing the number of protons in the nucleus. And when you increase the number of protons in the nucleus becomes stronger. And therefore, it pulls on that second shell much more tightly. For example, when I'm going from lithium all the way to neon. So I'm adding one more proton to the nucleus, it shrinks. When I go to boron, I add one more proton to the nucleus. It shrinks that electron cloud in closer, and it shrinks and shrinks and shrinks and shrinks and shrinks until I add a third shell, and then it gets much bigger. Okay, and then the trend repeats itself. It shrinks again, and then when I add the fourth shell, it gets bigger. I don't know why I'm making these sounds, but that's essentially how it works. Is you add shells, but you're also adding protons to the nucleus as you go across a period. Your largest elements, therefore, are going to be down here: cesium and barium, rubidium and strontium, very, very large atoms. The next trend is ionization energy. And the ionization energy is the energy that's required to remove an electron from a neutral atom of an element. The energy required to remove an electron from an element. So again, I'm going to skip to this image here. So this happens to be some element. It really doesn't matter what it is. But here I have one electron, or I have two electrons rather, in its outermost shell. So this must be an alkaline earth metal. It takes a certain amount of energy for an atom to lose an electron, because those electrons have somewhat of an attraction to the nucleus in the center, because the nucleus is positively charged and your electrons are negatively charged. It takes a certain amount of energy for that electron to go away. And we call that energy, its ionization energy. How much energy is required to remove an electron from an atom or element? And it differs, of course, because this is a periodic property. So what's the group trend? What's going to happen to ionization energy as I go down a group? Is it easier to remove an electron for those big elements at the bottom? Or is it going to be easier to remove an electron for small elements? Well, it actually decreases going down. It's much easier for big atoms to lose their electrons. And again, this has to come down to the size. Why is it so much easier for barium to lose an electron as opposed to magnesium? Barium is much bigger. That distance from that outermost shell is very far from the nucleus. And because it's very far, it doesn't take a lot of energy to take an electron away. So the electrons that are farther from the nucleus are much easier to remove. As you add shells going down a group, those shells get farther from the nucleus, and therefore it's much easier to remove an electron from one that's farther away, because that nucleus doesn't have as strong of a pull on it. And actually, it's very similar as I go across a period, because you can also think of this in terms of atomic radius. What's going to happen as I go across a period? It gets harder for atoms to lose electrons. It increases going from left to right, generally speaking. There's a couple of anomalies. We're not going to talk about those. Generally speaking, it gets more difficult for atoms on the right side of the periodic table to lose their electrons. Why? Again, because as I go across, you're adding protons. Those protons don't want to get rid of electrons. They're attracting the electrons and they're making them come closer to them. So therefore, it's harder for an electron to leave. In fact, these atoms on the right side of the periodic table, they don't want to lose electrons. They would much rather gain electrons. They say, heck yeah, come here, right? We want all the electrons we can get because we have a very strong nuclear charge and we don't have a lot of shells around the outside. So the increasing positive charge pulls the outermost electrons in closer, which therefore makes them much harder to remove. So like I said, we can also relate this to size. The bigger the atoms are, the farther away those outermost shell electrons are from the nucleus. And because they're so far away, it's very easy to remove them. It's going to be much harder to remove an electron from radon, even though they both have 6 shells around them. But because I have all of those protons in the nucleus, they're able to pull that 6th shell in, and therefore they're attracting those electrons much more. Which brings us to the last trend of electronegativity. So it's basically the opposite of ionization energy. Electronegativity is a measure of the ability of an atom to attract electrons. How bad does an atom want electrons? Not get rid of them. How much does it want an electron? So this is kind of a silly image, but so here I have some atom that's attracting electrons. It's pulling electrons towards itself, not getting rid of them like ionization energy, but pulling electrons towards themselves. So what's the group trend? Again, think of it in terms of size. If ionization energy, if it's easier to remove an electron going down a group, then do those atoms want electrons? No, they would much rather get rid of them because it doesn't take a lot of energy to lose an electron. In fact, that's why your alkali metals are so darn reactive, is because they're practically giving their one electron to whatever is going to take it that's nearby. They say, please, I don't want this one electron. Get rid of it. Whatever wants it can have it. So as I go down a group, the ability for atoms to attract electrons goes down. And that's because there is a larger distance between the nucleus and the outermost electrons. And therefore, those atoms don't want electrons as much. Again, the atoms get bigger. The nucleus is farther away from that outermost shell. Because the nucleus is so far away, it can't attract nearly as well as a much smaller atom can. This all comes down to size when we're talking about atoms and whether or not they want to lose or gain electrons. So speaking of size, what's the period trend? Well, electronegativity increases going across a group or across a period, except the noble gases. The noble gases actually don't want electrons because what's the one property of the noble gases that we talked about? Noble gases aren't reactive. They don't want anybody's electrons. They're very happy the way that they are. So your most reactive elements or your most electronegative elements are your halogens, actually. And that's because, again, the closer that nucleus is to that outermost shell, the more it's able to attract an electron. We can also say the closer an atom is to having a full outer shell, the more it wants the next electron. Fluorine needs one more electron to be super stable like neon. And fluorine's going to do just about anything to get that one last valence electron. It is super electronegative. In fact, fluorine is the most electronegative element on the periodic table. That's why fluorine is so reactive. It wants anything. It wants to get an electron from anything. And the same thing goes for all of your other halogens. They want to be just like the noble gas right next door. They're going to do whatever it takes to gain that last one electron. So the closer an atom is to having a full outer shell, the more it wants that next electron. Again, in terms of size, as I go across a period, that nucleus is much closer to that outermost shell, and therefore they're going to attract electrons. Again, in terms of size, so these small elements here, right, except for these guys are not electronegative at all because they are already stable. They're unreactive, they have a full outer shell, they're very, very happy. As I go down a group, so I'm increasing the atomic radius. So therefore, the distance from the nucleus to that outermost shell is increasing. Therefore, that nucleus doesn't have as strong of an attraction for electrons because there's a much bigger distance from the outermost shell to the nucleus. So your most electronegative elements are going to be towards the top. These guys want electrons more than the elements at the bottom. However, fluorine wants electrons significantly more than lithium, again, because fluorine is smaller. Look at the distance from the nucleus to that outermost shell. It's very, very small in comparison. So therefore, fluorine's going to do anything to get one more electron to be like neon. Chlorine's also electronegative, but not as electronegative as fluorine. It also wants one more electron to be stable, like a noble gas argon in this case. But there's a bigger distance from the nucleus to that outermost shell, which gives it less of an ability to gain an electron. And the same is true going down a group. This is quite an abstract topic, so we are going to do quite a bit of practice with this. We're actually not going to do sample problem 4 in a video. We're going to do that in class because I definitely want to talk about that and get a feel for how you guys are understanding this. But this is really the big idea behind the whole periodic table is periodic law, periodic properties. And these 3 in particular are super periodic properties. Write down any questions you might have for me, put a star next to something. Like I said, we're going to talk about this in class and do lots of examples. So don't be overwhelmed if you are feeling like, oh my God, I have no idea what she's talking about. We're going to talk about this in class, I promise. So that's it for this video. I hope it wasn't too long, but I will see you guys in class the next time I see you, and then I'll see you in Unit 4. Have a good day.